Hey everybody, this is Mr. Bowman. So today's looking at the triangle congruence, specifically SSS and SAS methods. And these are a little odd in how they set them up in ALEC. So I figure we could just go ahead and look at it straight in here and see how it goes. So looking at these, whenever you start this, it's called a two-column proof. So there's going to be a column here that's statements, and then a column for the reasons for why we're allowed to say this or state this or change this or whatever. So what they're going to be in a single one. So this one has to be a given statement. So I get two, in this case, given statements. So I look at which one starts with RS. So this top one, line segment RS, is congruent to line segment TU. So to finish this up, I just need to put in the TU. Okay. And then my next one is ST is congruent to UR, which is listed here. The reason I'm going to do anything in this section is given. That's basically like the original problem they gave you. Okay. Now this is a common scenario where you use something called the reflexive property. The reflexive property, in a nutshell, does one of two things. It either says that a number is equal to itself, or that a shape is congruent to itself. So if I'm using the reflexive property, it's saying that RT has to be congruent to RT. It has to be the same thing. Okay, so now let's see what we're actually looking at here. So here we have RS is congruent to TU, which are kind of our top and bottom lines. ST is congruent to UR, so our kind of right and left lines. And then RT is congruent to RT, which is our line that cuts through the middle. So I'm looking at the triangle RST and the triangle TUR. So I'm trying to prove those congruent. So I'm looking at which reason it's going to tell me why. So in this case, I'm looking at my other three lines because those are all congruent statements and looking at, are they angles or are they sides? In this case, all three of them are sides. So that means I have to scroll down to my SSS congruence property for side, side, side. Three sides that are congruent. Okay. So now looking at this one, this is another very common one. But let's go ahead and get the first three lines down first, and then we'll talk about what property it is. So this bow tie shape, though, is pretty common. So looking here, I have EF is congruent to GF, which is one of my given statements. And then my other one, given DF is congruent to HF. All right. Now this one is saying the angle DFE, so this guy right here, is congruent to HFG, which is this guy on the opposite side. Whenever you have an intersection, the two angles on opposite sides have to be congruent by the vertical angles property, okay? Because they are vertical angles. And this applies to either intersection. So in this case, we're looking at left and right, but the top and bottom ones are opposite as well and would also have to be congruent. They're just not relevant for what we're doing right now. But either one of those is still the vertical angles property. So now looking at this, I don't have three sides this time, so it's not SSS. I have two sides and an angle. So to make sure this works, I need to look at where they are. So I have EF, and I have DF, and this angle DFE. And I really like to look at one triangle, which is why I'm just looking at the EFD triangle. So I have side, a side, and the angle that touches both of those sides. Since that angle is then in the middle, that is the SAS, or side angle side property, which is enough to prove congruence. Okay, so that's how these ones kind of set up.